Following on Andrew's post the other day about delta P and square law, I just did a short video that might explain a bit of an anomaly in the square law. Um, if you take a pipe uh, with P1 at one end, and there's no velocity through the pipe, there's no pressure loss through the pipe. So no velocity, no pressure loss. So once you have any velocity, you have to have a pressure loss. Now there are lots of formulas for governing pressure loss, um, but basically they're all basically the same. So here's one. It's the Darcy-Weisbach, and it basically states, I've given the references below if you want to study this in more detail, but I just want to explain the anomalies. So the delta P, which is the pressure drop per unit length, call it per meter, is equal to a function called the FD, which is the Darcy-Weisbach function. Now this is where the anomaly arises. This is it's a fixed variable, which is an oxymoron, but I'll go into that in a minute. But for all intents and purposes, you can take it as fixed. So the only variable is P is rho is the density, and D is the diameter, which is fixed, and V is the velocity, which is the only other variable. So basically, in this formula here, the only variables are V, and that gives you the delta P. That's translated then into Q, which is basically the same as flow. Uh, now, this is where the anomaly arises a little bit, and where this factor here is governed by the Reynolds number. Now, the Reynolds number has a lot of different variables built into it: pipe friction, wetted surface, a whole lot more, which are covered in the references below. So this is really where the difference arises. For laminar flow, which has a low Reynolds number in a circular pipe, the friction factor is inversely proportional to the Reynolds number. In effect, the friction loss in a laminar region is more accurately characterized as being proportional to the flow velocity. Remember, this is laminar flow, not turbulent flow, rather than proportional to the square of that velocity. So one can regard the formula as really not applicable, but it is. So I'll explain now. So this is a chart showing the constant, the Weisbach constant up here, the Darcy-Weisbach constant, as a function of Reynolds number. So you see with laminar flow that it drops off linearly, but now this is a log function, so it's actually the counter of the square. So that is, as that gets bigger, which would equate to the velocity getting bigger, it's actually getting smaller, which counters it. But that you arrive then at this point here where you get turbulent flow, and you can see that the variable function is now constant for different pipes. They're all different types of pipes, copper. So basically, once you go beyond that threshold and you have turbulent flow, which most systems will have, you get the square law is correct. There's the, if you want to read that in more detail, there's the reference for it. I hope that might clear up some of the misunderstandings or doubts that might be out there.